So that was based on flow arrangement, but now let's see classification of heat exchanger according to transfer processes. Let's see according transfer process. So the first one is indirect contact type and direct contact type. Indirect contact type, that also refers to surface heat exchanger. In this type, fluid stream remains separate. The fluid separate and the heat transfer takes place continuously through separating wall. There is a wall in which the wall is separates the fluid from the heat. So the heat passes through the separating wall. So we can say there is no direct mixing of fluid because each fluid flows in a separate fluid passage. So we call it indirect contact type. So as long as there is mixing of fluids, we call this indirect contact type. So let's see classifications of indirect contact type. The first one is direct transfer type, and the second one is storage type. The third one is fluidized bed exchanger. So direct transfer types. In this type, the hot and the cold fluid flows simultaneously through the device and heat is transferred through a wall separating the fluids. Most of the time, we have tubular, plate type, extended surface exchangers. But the second one is storage type. That also refers to regenerative heat exchangers. These storage types are most of the time, we call them regenerative heat exchangers. So this type of heat exchanger has a heat transfer surface flow path which is generally cellular in structure and refers to as matrix or is porous solid material for the storage type, indirect contact type heat exchanger. In this, both fluid flow alternatively through the same flow passage. When the hot gas flows over the matrix, the thermal energy from the hot gas is stored in the matrix wall, and those hot gas is being cooled during matrix heating point. Right? When the matrix is heating, so this hot gas is being cooled at the same time. So we can say in this type, the corresponding thermal energy is alternately stored and released by matrix wall. So this thing is playing a good point here because it is alternatively storing and releasing in the matrix wall. The other thing we have fluidized heat bed exchangers. In fluidized bed heat exchangers, one side of a two fluid exchanger is immersed in bed of sand or coal particles. We have to immerse it in bed of sand or coal particles. And at optimum fluid velocity, the bed particles float and the condition is referred to as fluidized condition. This is why we call it fluidized condition. When the bed particles float and the condition is referred to as fluidized condition. Leads to floating of the bed particles. Under this condition, very high heat transfer coefficients are achieved. So here one thing that really interesting is very high transfer coefficients are achieved. Most of the application of this fluidized bed exchangers are in drying, mixing, adsorption, reactor engineering and cold composition. And the second one is direct contact type. So two fluids are not separated by a wall. The heat transfer takes place between two immersible fluids like gas and liquid. So there is no separate wall here. So we have to have immersible fluids like gas and liquid coming into direct contact. So that's why we call it direct contact type heat exchanger. So let's see the direct transfer types. We have different types. The first one is we have tubular heat exchanger. We have plate heat exchanger. So in tubular heat exchanger, we have these two kinds and we will try to cover them on the next slide. So let's start from tubular heat exchanger. In tubular heat exchanger, shell and tube heater is the simplest form of tubular. Shell and tube, this one is like the simplest form of tubular heat exchanger. We can have, or we can see the construction. First, tubular heater consists of a bundle of parallel tubes inside the cylindrical shell and two distribution chambers, chamber D1, chamber D are provided at each end of the casing C. We will see it here. We don't have the real construction of this shell and tube heat exchanger, but like I want you to focus on the definition now. And fluid inlet is provided at chamber D2 and chamber the outlet is at D1. Like as I said before, we don't have distribution chamber 1 and distribution chamber 2. So we will see how this really works on the next slide. And provision from escape the non-condenser vapor K and condenser vapor K to drain at G. So let's go here. This is like two fluids can exchange heat. One fluid flows over the outside of tube, while second fluid flows inside tube, right? One is inside the tube and the other one is outside the tube. So as you can see here, we have the distribution chamber, we have side cover here, we have the inlet of the cold fuel and the outlet of the hot fuel, and we have the steam inlet and we have the steam outlet. So what we are going to see here is we're going to focus on their construction and their working principle. So let's cover it here. So steam or any vapor introduced through steam inlet. Through the inlet, there is steam introduced into space surrounding the tube, and the steam flows down the tubes. So after the steam comes here, it starts moving here, right? In this process, the tube gets heated rapidly due to high value of steam film coefficient. So here we have the tubes, right? These are tubes. So due to this steam, the tubes starting getting hotter and hotter. So the condensed vapor drains through condensed outlet. So the condensed vapor drains through the condensed outlet at G. We have the condensed outlet at D, which is kind of drain here. And then non-condensed gas, if any, escapes through vent K. If it is non-condensed, it escapes through this vent K. The fuel to be heated is pumped through the cold fluid inlet H into distributing chamber 2. And then the fluid flows through the tubes, and then the fluid flows through the tubes. The fluid in tube gets heated due to heat transfer by conduction, right? Followed by stagnant layer and finally by convection. This enhances the rate of heat transfer. At first, it was by conduction, then it becomes by convection, which is kind of enhancing the rate of heat transfer. And then we have heat fluid reaches distributing chamber D1 and leaves hot fluid outlet I. So we have the distributed chamber 1 here, and the outlet will be here, like at the end of the process. This is what really happens. And mainly its application of this kind of shell and tube heat exchanger is in pharmaceutical, petroleum, refining and chemical industries as steam generators, condensers and boiler feed water heater. And also we use it in air conditioning and refrigeration applications. And if we see some of the advantages of this kind of heat exchanger, we have they are most versatile exchangers made from variety of metal and non-metal materials. And the tubes are replaceable and can be easily cleaned. This one is a good item. If you want to, you can easily replace the tubes and you can clean them so easily.